So what is association rule mining? Given a set of transactions, find rules that will predict the occurrence of an item based on the occurrences of other items in the transaction. So association rule, first we understand based on some market transactions done at a supermarket or some store. So this can be extended to many other, even it can also be extended to the classification algorithms also. So initially, this is also called market basket analysis. So now, what is this association rule? Analysis is nothing but, can we say that if a basket has, suppose diaper, it also will have beer, something like that in that basket. Most likely that people purchase, whenever they purchase diaper, they will also purchase beer. So if you see your examples of association rules, right side, there are some rules. So that means that whenever they purchase diaper, there is more probability that they will also purchase beer. Whenever they purchase milk and bread together, then eggs and coke also will be there in that basket, most probably that. The most probably means it is not 100%, but most of the times they are purchased together. So if you see the left side, that is the transaction data. So somebody purchased bread, diaper, beer, eggs, then third person purchased milk, diaper, beer, coke. Based on this, can we find some rules so that we will predict the occurrence of an item based on other occurrence of other items in that transaction? In other words, it is also called co-occurrence. Implication means co-occurrence, not causality. If you see repeatedly same composition, then it is not simply co-occurring, it is co-occurrence, but there is no reason. People try to find out why do they purchase. If they want to find out reasons, they can try, but there is no specific reason that when they purchase diaper, why do they purchase beer? Or when they purchase beer, why do they purchase diaper? Then people may come up their own reasons, why people more tend to purchase them together. So first we will define what is frequent item set in a transaction. So the item set means a collection of one or more items in the previous transaction data. Milk, bread, diaper is one item set. K item set means an item set that contains K items. So item set is simply a subset of all items sold in that or available in that supermarket. You can think like that. Then K item set means a subset of cardinality K. Then how do we count? Support count. One more term we are introducing here, support count. Frequency of occurrence of an item set. How many times in the transactions that item set appeared? That how many times is support for that item set? How many times in transactions we have seen that item set? Means those items together in transactions. So if there are more times you see, that is more support. If you see less times, then less support. Example, you see the right side data set. What is the support for the milk, bread, diaper? You see all the transactions and find out in how many transactions you find these three together. Milk, bread, diaper. First one is not there. Second one is also not supporting this item set. What is missing in second one?
Milk.
Milk, sir.
Milk is missing. The third one is supporting this. No.
Bread. Bread is
Bread is not supporting. What about the fourth one?
Yes.
Yes.
And
Yes,
fifth
sir.
one
Yes.
is
Yes.
support.
Yes, sir.
So what is support of this item set in this transaction data set? Two transactions is supporting, so the support is 2 year. What is frequency of bread in this transaction data set?
4, sir.
4.
So first one, second one, yeah, 4. So that is, so bread is more frequent. If you get the frequent, then bread is, if you take single item set, then maybe bread is the more frequent. Am I right? See for other items, what is frequency as a single
Sir,
item set?
diaper also 4, sir.
Diaper. Even milk also, sir.
Even bread also 4.
Bread.
Yeah. So there are many with, is there any with 5?
No, sir.
No, sir.
How do you eliminate easily? If bread is not 5, milk is not 5, then there is no question of any other thing can be 5, right?
Yes, sir.
That is support count. Support will come in fractions. So 2 out of 5 items are supporting this particular item set. Then support we always say in a fraction. The total number of support count, the support count by total number of transactions is support. So fraction of transactions that contain an item set. So in the above case, there are 2 transactions out of the 5 transactions that are supporting. So support in terms of the fraction is 2 by 5, that is 0.4. Support count is different, support is different. Support is always a number between what?
0 and 1.
Because you never get numerator bigger than the total number of transactions, right?
Yes.
That is the maximum, that is 1. So when do you get minimum?
When there are 0
Zero support
occurrences.
count.
No transaction supports. So the value, can you go below them 0? You cannot,
No.
right?
No, sir.
Because it is a counting thing. So you cannot count anything less than 0. So what is the meaning of frequent items? An item set whose support is greater than or equal to a min sup. This can also be read as minimum support threshold. So we define an item set is frequent. Then first we define a threshold. If that item set has support more than that minimum support, then that item set is called frequent item set. So if I define threshold as 0.3, then this item set milk, bread and diaper, will it become frequent item set?
No, sir.
No, sir.
It becomes 0.3, I said, right?
Oh, yes, sir. Yes.
So then what is this 2 by 5 is? 0.4.
0.4.
0.4.
So it becomes then if I define my threshold as 0.5, then it won't. So this is always relative, which are frequent item sets, which are not frequent item sets. Based on the threshold, minimum support threshold, we will compute them. Okay. Then what is association rule? An implication expression of the form X tends to Y, where X and Y are item sets. So association rule is always a relation between 2 item sets, whether one follows the other or not. So association rule means you need to have 2 item sets. Here X and Y are given. X means milk and diaper, 1 item set. Y is the another item set, beer. Rule evaluation metrics. How do we define this rule? Whether it is an association rule or not, how do we define? First of all, we need to see support. Fraction of transactions that contain both X and Y. So support, to compute the support, we need to take first X union Y, then see how many transactions support X union Y. How many transactions support X and Y, not individually, together, X and Y together. That is the support of the association rule. Whatever rule we are going to make, that rule will have a support. That support is nothing but all the items involved in that rule. What is the support count for that item set? Then the second part is confidence. Measures how often items in Y appear in transactions that contain X. First, we should get the support count for the entire item sets combined together, X and Y. Then, whenever a transaction support X, what is the probability that that also support Y? In other words, how many times you see X in the same basket, you can also see Y in terms of the fractions, confidence means. So, okay, we have seen X 10 times in the same support. If we see those, let's see which transactions are supporting this X 10 times in the same transactions, if you see Y also 8 times, then confidence of Y will be, confidence of this association rule will be 8 by 10. That is nothing but support of Y divided by support of X. The support to be considered as which support for both X and Y. So you take the example, it becomes clear now. Milk and diaper, we want to make a rule, then we will see that whether it qualifies or not, or first we compute what is its support and confidence for this rule. If you take milk and diaper, that implies beer also, here. Then support, how do we compute the support? How many transactions are supporting this item set milk and diaper divided by total number of transactions. This already we did in the previous slide. So we got 2 by 5 equal to 0.4. Then how do we compute the confidence? Support of milk, diaper, beer. Okay. Then support of milk and diaper. In the same support set only we need to see. So here support of milk, diaper, beer is 2. So in how many transactions you have? Okay. This is the support of the entire item set, right? Milk, diaper, beer. So count this, how many times you get this milk, diaper and beer?
2 times.
Already we counted, that is 2 times, right?
Yes.
Then what is the support of the milk and diaper? Count here from here.
3.
3. So you are getting 0.67 is the confidence. What does it say? Whenever people buy milk and diaper, 67% times they will also buy beer. You understand how to read this rule?
Yes.
Then the question comes that how many times you observed? If only one time it happened, let's say, all milk, diaper, beer, and no other time they purchased it, let's say, then we'll say that, oh, I observed so many times. In that observation, so many observations, I'm getting 67%. Then the rule will have more confidence. If you don't have enough support, let's say, suppose let's say you take simple example in probability. If you toss a coin only once and you found a tail, based on that you cannot say that it's 100% times this will give tail, because it's 1 out of 1 I got tail. Then people ask immediately how many times you tossed that coin. 1. Then they'll not consider that as a good example, let's say, to compute the whether coin is biased or not. They'll ask you, let's say, do the 100 times, then come. Then you may say that 49, 51 times, then it is almost the same. So it is unbiased. Here also it's how many times you have seen purchasing milk and diaper? 2 times. Along this, how many times they purchased beer? 2 times. So 100% they purchased together. Then the question comes that it's okay, you observed only 2 times. 2 times may not be that important. There will be many transactions. So out of those transactions, if you it so happened so that it's randomly they might have purchased those two. If that you say that it's there are 100 times I have observed that whenever they purchase milk and diaper, there is more probability that they also purchase beer, then that rule will have more confidence. So association rule mining task, what is this problem we are going to do in this is, given a set of transactions T, the goal of association rule mining is to find all rules having support greater than or equal to minimum support, that is threshold, confidence greater than or equal to minimum confidence threshold. So this is again, it's a user given inputs. There is nothing like it's a, it depends on what problem you are taking, what domain you are taking, how important that rule to extract it, say. So if that rule to be more valid, and based on that, if somebody is going to take some decisions, then they may require more support and more confidence also. Or else it's a, if they don't need more support, more just a trend, then they may say that it's a, even if with little minimum support and little minimum confidence, the rule is good for me, I can do some analysis based on that, I can improve my business. Then it's a, they can have lower number of minimum support and minimum confidence. Again, it depends on the problem and domain where you are working. Suppose if it is a healthcare, what diseases come together? If somebody has a high blood pressure and high diabetes, then what other diseases comes together? Then let's say people may not need more confidence, means okay, 50% confidence is also okay because I can alert them. Other diseases follow because you have already these, we have observed in all the patients, whenever they get these two, then other disease also may come, so you need to take care. Then they don't need to take the more confidence, right? But if they want to start the treatment, it's a whatever that it's in, what they say, preventive treatment. They may need more confidence. Why?
Because
To alert, they may not need more confidence, but to start the preventive treatment, they may need more confidence. Why?
they would need to spend money on it.
Not only money spent, right? Other complications also will come, right? Whenever you're taking treatment.
Right.
You put lots of chemicals, all those things. And it's only 50% confidence you have, then 50% people you are suffering without, they may not get that, but you are starting preventive treatment. Then they need to assess that it's the trade-off. Then how much those 50% people who may not get that disease may be troubled with this preventive treatment, those things. It depends on the domain and the problem where you are looking these rules. So that's why it is user input, and based on the problem they understand, they may fix this minimum support and minimum confidence. Then how do we find these association rules? Then the first approach is the brute force approach. List all possible association rules. So if there are 10 items, how many rules you can form? Is there any limit that it's a left side set should be this much, right side set should have these many elements in X and Y? There are no rules on X and Y, right? So they are simply subsets of the given data set. So how many rules you can form with three? We'll go with smaller thing. With 3 items, how many rules we can form?
3 rules.
Suppose A, B, C are items. Then how many we can form? A implies B, A implies C. B implies C, B implies A. C implies A, C implies B. That is 1, 1, right? Then you can start AB implies C, BC implies A, CA implies B. 2 by 1.
2 power.
And 1 by 2 also you can do. A implies BC, B implies CA, C implies AB. Then
2
how do
power
you
n.
compute? Yeah, 2 power
2
n.
power n. Minus 1, we're removing the empties.
Okay, 2 power n subsets you have, right?
Yes.
Then combination also will come now. Left side one, that is left side can be any subset, right side also can be any subset.
Right.
Then 2 power n C2 then.
Right.
So C2 is again a square complexity, right? So 2 power n whole square, 2 power n plus 1.
Right.
So we will see that there are some more problems will come, because whatever the items you have left side, those shouldn't be there in the right side set. Because you are looking whenever these items are there, what other items will accompany them, right?
Right.
So same set you cannot write x implies x. Then that will have 100% confidence. So with those rules, you can see here, total number of item sets is 2 power d, provided d is what? Number of items in the whole transaction data set. So this part you did correct, 2 power n. Instead of n, we are using here d, okay? Then total number of possible association rules equal to, this k is equal to 1 to d minus 1. And dck, because left side first you are writing, left side how many you can take, minimum one element to maximum d minus 1. Why
D
can't you
minus
take
1.
the maximum set with d elements?
There should be some other element in the y items.
Right, to find out, otherwise it's empty only will remain, that won't form any rule. So maximum you can take only d minus 1. So that is nothing but k is equal to 1 to d minus 1. So how many ways you can select a set with one item? There are d items. So you can select DC1, 1 sets. How many 2 sets you can find out?
DC2.
DC2.
How many k item sets you can find out? DCK.
DCK.
That is left side. Then right side. The right side we have already told that the elements which are there in the left side shouldn't be there. And how many elements you have now to select the right side set?
D minus k.
In each case, if you already selected k for the x, then d minus k are available for y. So this, as k changes, d minus k also changes. If k equal to 1, this is d minus 1 available. If k equal to 2, d minus 2 are available. Then out of d minus 2, again you can select 1 to d minus k elements.
Right.
So this is a product rule, right? First one you can select k is equal to 1 to d minus k dc. First one you can select dck. Second one you can select d minus k by d minus k cj. So according to the product rule, dck versus all those things will come here. Then for each k is equal to 1 to d minus 1, you are summing up. If you expand this, let's say, anybody remember what is the formula for nck? N factorial by?
N minus k factorial into k factorial.
So if you want, you can extend and see that, let's say, how good your aptitude skills you gain. Then you should get this result, 3 power d minus 2 power d plus 1 plus 1. So it is not simply 2 power d. If we consider highest, what is the highest, whether 3 power d is highest, 2 power d plus 1 is highest?
3 power d is highest.
How do you get that?
So
Then
because
you need to,
3 is greater than 2 and d is always positive as it is count. So if we increase the d value, the gap between 3 power d and 2 power d will diverge, sir.
yes, simply you can take 3 by 2 fraction, make d plus 1, power d plus 1. Okay, then you can see that you can write 3 by 2 power d and 1 by 2. So 1 by 2 is always constant, right? If I write 3 by 2, 3 power d by 2 power d plus 1. See, if I write this as 3 by 2 power d into 1 by 2. So I am comparing what numbers? Both are positive, right? 3 power d is positive and 2 power d plus 1 is also positive.
Yes.
So I can compare. If I get less than 1 value, then numerator will be small. If I get greater than 1 value, then numerator is big, right? So then you see 3 by 2 is how much? That is 1.5, right?
Yes, sir.
So 1.5 power d by 2. So 1.5 is bigger than 1. So as you increase the power, this will become infinity, right? This goes to infinity. 1.5 power.
Yes, sir.
But you are still at this 1 by 2 is means infinity by 2 is infinity. So you are getting this whole fraction infinity. So 3 power d is very big number when compared with the 2 power d plus 1. So the complexity is more than 2 power d. So why are we computing this? What is the heading of this slide? Why are we computing this, right? How many rules we can form?
Based on the number of items in our collection, how much computation that we need to do to find the association rules between the items.
So if you go by brute force approach, then you need to find out all probable rules. This is just how many probable rules we can find. Still after that, there is something, again, you need to get the support count, confidence count, all those things, right?
Right.
Just many rules you need to find out whether that has enough support and enough confidence or not. So what it tells us for us, this computation, it tells us that it is not feasible most of the times. If number d increases, then it goes to high complex problem with respect to time. So this brute force approach is not a feasible approach. The solution is possible, but approach is not feasible. You understand? That's why we are saying that it's a this much of complexity will come. Be careful, let's say, to apply this brute force approach to find out the association rules. So there are some rules are given here, mining association rules. This is a small data set. How many? What is D here? Count.
5 total number of items.
Only 5. 1, 2,
5, 6 coke.
4, 5. Coke is 6.
That's it.
I think 6. So according to that, 3 power 6 minus 2 power 7 plus 1. How many that is?
6 not 2.
3 power 6 minus 2 power 7 plus 1. So anybody has calculated? 3 3s 9, 9 9s 81, 81 9s is how much? 8 9s 720.
729.
729. 729 minus what is 2 power 7?
128.
128. Okay. So 729 minus 128 means 601.
Not one. Yes.
02. D, here it is computed already. So 602 rules. So actually, it's a real rules. First of all, it's a possible things. Maybe that's 602, but it's a you may not get that many valid for any minimum support and minimum threshold. So it is a futile exercise to get it's 7 or 8 rules. Finding 602 rules and finding their support, their confidence, those things. So here, how many rules you are getting out of this? Only 5 rules you are getting, 5 or 6 rules you are getting. So to get these 6 rules, you are finding 602 rules first. Then for each rule, finding its confidence, its support. So that becomes a futile exercise. That's why here this example is given. Actual rules are only this with these supports. So we will take 1 or 2 and see that it's whether they are saying correct and do we know how we can compute this support and confidence. So take the last one, milk. Then how do we get the support? Support to be taken.
Support count by total number of transactions.
Support of what count?
Milk
Support
count.
what? Item set combined together, both item sets. Milk, diaper, and beer, right? That is the support count. See, your formula is support is the milk, diaper, beer. So you need to take the union of X and Y. Milk, diaper, beer. What is support divided by total number of transactions? That is yes. C is then again support of all those things, then support of the X. Okay, what is support of milk, diaper, and beer in this?
2, sir.
I am trying to very
2 by 5.
Two, sir.
milk, diaper, and beer. The second one is not supporting. Third one is
Third.
support.
Third and fourth, sir.
Fourth. Okay. So 2, right? 2 by 5.
2 by
That
5.
is 0.4.
0.4.
Then how do we get the confidence? This is same. Support count of this, that is 2 divided by
4.
support count of
4.
what?
Diaper and
Milk.
beer.
No,
Milk,
support
milk.
Oh, milk, sir. Milk.
because we are looking how many times milk comes, diaper and beer follow. So support count of milk. How many? How
Milk.
much that is?
4.
4.
2, 3, 4. So 4 by
2 by 4. Sir.
2 by 4.
4. So 2 by 4 is the 0.5. So all the above rules are binary partitions of the same item set. What is the meaning of binary partition? Binary means how much?
2.
2. So if you take only 3 binary partitions means it's partitions of the same item set. Milk, diaper, and beer is giving these 3 milk, diaper, and beer. Then you make 2 partitions. In one side 1 element, other side 2 elements. That is what we did here. That is what he is saying here. Rules originating from the same item set have identical support but can have different confidence. So how do we qualify this? Rules originating from the same item set have identical support but can have different confidence. Because support is counted putting together, right? When you are putting together, then your set will become always milk, diaper, beer. That's why your support is always 0.4.
Right.
But support of the individual means subsets of these item set may be different. That's why you are saying different confidences. So with high confidence, you are getting whenever they purchase milk and beer, they will also purchase diaper. It's most probably it's a milk for the kids, beer for the elders. Then both people need diapers because one person may not know that it's other person may lose his consciousness. That's why the people, they may want to have diapers. So whenever they purchase this, they purchase diapers. Something it's reasoning, if somebody is wanted, they can try to find out reasons why. But as a data scientist, our main aim is to find the rules, not the reasoning. So thus we may decouple the support and confidence requirements. So if minimum support required, then first we need to see X union Y should have that support, minimum support. So that's why we decouple. First of all, we will find out all item sets for which we have minimum support. From those item sets only, we try to find out association rules by dividing them into. So if the item set, let's say combined item set itself is not having minimum support, there is no need to find out any rules based on that, because anyway you will have less than the minimum support. So that's why we can decouple the support and confidence requirements. So we will take two-step approach instead of the brute force. One is the frequent item set generation. So first we will find out all frequent item sets. From those frequent item sets only, you should be able to find out rules. Otherwise, you cannot find any rules if the set itself is not frequent item set. Generate all item sets both support greater than or equal to minimum support. Then rule generation, generate high confidence rules from each frequent item set, where each rule is a binary partitioning of a frequent item set. Frequent item set generation is still computationally expensive anyway. See, to get one item implies other item, what frequent item sets we need to search? Is my question clear?
No, sir, can you repeat the question?
The question is, we want to have rules. It's association rules where X is also one element, Y is also only one element. Means milk implies diaper, beer implies diaper. So cardinality of X is 1, cardinality of Y equal to 1. For my association rule, I am putting that restriction. Then what frequent item sets I need to find out to get those rules? So first X union Y should be frequent, right?
Right.
So how many elements X union Y will have?
2.
Only 2 elements. So I need to see what are the frequent 2 item sets. From them only I can find one item implies to other item, right?
Right.
So to get the rules with only 1 versus 1 or 1 implies 1, I need to see only 2 frequent 2 item sets. Similarly, if your association rule is having 3 item sets putting together, I need to see only frequent 3 item sets, frequent 4 item sets. So like that, so that's why first frequent item set generation, first you get the frequent item sets of 2 items. So that will generate simple association rule. One item implies to another item. Only will a 3 item set is frequent, but subset of that is not frequent? Can you find like that? A 3 item set, it is frequent, but its subset of 2 items is not frequent. Can we find such a situation?
No, if 3 are appearing, 2 will also
then 2
appear.
also appear in all those things, right? 2 may have more support than the 3 items.
Right.
So if 2 item is not frequent, then there is no meaning of adding one more item to the 2 infrequent 2 item set and whether that becomes the frequent item. Because it is not supporting 2 means, how can it support another element joining that, right?
Right.
So we can reduce that, 3 item sets lesser than the frequent 2 item sets. From frequent 3 item sets only, we will extend to the find adding one more element and see whether they are frequent 4 item sets like that. Okay. So how people will generate these frequent item sets? We'll get that algorithm now. So rule generation, generate once you get the frequent item sets, then take the partitions, then find the confidence. Then you will get the rules, provided that confidence is more than the minimum confidence. Frequent item set generation is still computationally expensive. Here it is given again pictorially. Then one frequent item sets A, B, C, D, E, 1, 1. Then A can be extended to AB, AC, AD, AE. Then B can be extended to BC. Why not BA is not here? Because already A covered AB, right? So B isn't required. Only you see the coming numbers. BA, BC, BD, BE, then CD, CE, then DE. Then E is already covered. So two sets will be this many. Then again, 3 sets will be this many. Then 4 sets will be this many. Given D items, there are 2 power D possible candidate item sets. How are you getting this 2 power D?
Total number of
subsets, right? So all subsets you are finding for the total. So cardinality of all subsets of a given set is the 2 power D.
Right.
So how do we generate a frequent item set? Brute force approach again. Each item set in the lattice is a candidate frequent item set. Count the support of each candidate by scanning the database. Count the support of each candidate by scanning the database. So first we will get the support of bed, support of milk, support of diaper, like that. It's a list of candidates. So item set 1, frequent item sets. Match each transaction against every candidate. The procedure is explaining. Take one candidate, then see that how many transactions are supporting that candidate. Then complexity is order of NMW, that is expensive since M equal to 2 power D. Match each transaction against every candidate. So this M item sets you have, right, to find out the frequent. So that is 2 power D. So this N is nothing but each transaction may have so many elements in that. So you need to see that it's each element to be compared with each element in the frequent item set. So if there are N items, then N items are to be compared with this. In other words, let's say there are W transactions and N items involved. So many comparisons takes place here, particularly. These N transactions are there because each transaction to be compared with item set, whether it supports or not. So N times means, see, one item set you take, all these N transactions to be verified whether they support or not.
Yes.
Do you agree that?
Yes.
So N times of number of item sets. Then what is this W? Within the transaction, again, comparisons will come, right?
Right.
So that is some average number you take. Average transaction size is suppose 7 or 8, whatever that it's in. Then this W is close to that. In some transactions less, some transactions more. So because each one to be compared with the item set elements. So that's why you are getting order of NMW. So because M equal to 2 power D, this is again 2 power N complexity. Exponential complexity. Whenever it comes to the exponential, then we shouldn't take that approach. Reduce the number of candidates. So instead of taking all possible things, now one way is you reduce. Just now I discussed, right? If one item set is one set itself is not frequent, one item set, then there is no meaning of computing item sets of 2, size 2, having this one element, because that one element itself is not frequent. So whichever is added to that, that also won't become frequent item set. So one way is reduce the number of candidates, complete sets m equal to 2 power d, use pruning techniques to reduce m. Then we'll see that how do we prune them. Reduce the number of transactions. Reduce size of n as the size of item set increases. So another way is, let's say, in this complexity, there are three parts are involved, right? One is the number of transactions. If you can reduce number of transactions, your complexity will come down. Another is m, number of frequent item sets you are trying to see. If that you can reduce, then this complexity will come down. Anyway, average transaction you cannot. So these two things we need to take care. Even they are saying that, it's say, how do you reduce the number of comparisons also? So reduce the number of transactions, n. Reduce size of n as the size of item set increases. So whenever your item set is having more, then you can also reduce the number of transactions. Means if transaction itself is having less number of items, then anyway it won't support more than its element in the transaction. It cannot support more elements, right? So that is how you can reduce the number of transactions. Use it by DHP and vertical based minimum algorithms. Some algorithm names are given here. Then another way is reducing the complexity, number of comparisons. Reduce. Use efficient data structures to store the candidates or transactions. So here they are saying that use efficient data structures so that you don't need to compare repeatedly the same things. No need to match every candidate against every transaction. Now, reducing number of candidates, there is a principle that is a priori principle. We will use this concept to reduce the number of candidates. What this concept says, if an item set is frequent, then all of its subsets must also be frequent. This is what just now we discussed. Because it is supporting 3 elements together means all those transactions also support any of subset of that. So that's why whenever a set of k or k item set is frequent, all its subsets, k minus 1 subsets, k minus 2 subsets will also be frequent. Then a priori principle holds due to the following property of the support measure for xy. X is in y implies support of x is greater than support of y. Means subsets will have more support than the supersets. That is the principle. When it is supporting 3 elements together itself, it will definitely support all 2 subsets of those 3 elements. So that's why support of smaller sets or supports of subset is always greater than or equal to support of superset. Support of an item set never exceeds the support of its subsets. This is known as the anti-monotone property of support. It's a mathematical term. Monotonically increasing means if x increases, fx also increases, the function fx is called monotonically increasing. If x decreases, fx, any function of x decreases, then that is called monotonically decreasing. Monotone means in a single direction, right? So illustrating a priori principle, then found to be infrequent. Then if AB is infrequent, then you don't need to find out whether ABC is frequent, ABD is frequent, ABE is frequent, ACD is these 3. ABC is frequent, ABD is frequent, ABE is frequent. Why? Suppose you found AB itself is infrequent.
AB itself is infrequent, ABC will also be definitely infrequent.
Yeah. They are supersets of AB, right?
Right.
Subset itself is not having enough frequency, then how can supersets will have more frequency than this? So they also will be infrequent. So that's why we will cut down all these things. If ABC is infrequent, then ABCD also infrequent, right?
Right.
So all this will go, once you find AB is infrequent, don't try to find out whether remaining things are infrequent. They will be infrequent whether you found or not. So that is how they are pruning this. So illustrating a theory principle here, minimum support you take 3. Then if every subset is considered, then 6C1, 6C2, 6C3, then you get 41 items. With support based pruning, you are getting only 16. Then how do you understand this? Okay, so item sets 1. First, we need to get frequent item sets, right? So we'll start with 1 frequent item sets. So here support count is given for each item. Bread is 4, Coke is 2, milk is 4, beer is 3, diaper is 4, X equal to 1. So your threshold is how much here? Minimum support? 3. Then which are infrequent according to this?
Eggs and Coke.
X and Coke are infrequent. Then you don't need to consider any supersets of X and Coke for our computation, right?
Right.
So they are removed now, the first. So we need to extend only remaining things as supersets and see whether how much support they will have. So items with 1 item sets. So bread and milk. Within these things, now you are trying to find out. Within these things, you are trying to find out rules. So if you take bread, bread implies milk, bread implies beer, then bread implies diaper. Then go down, milk. Okay, then they took the beer, right? The second thing, beer implies milk, and that's all. And diaper implies milk. These are the frequent item sets. So they are not considering milk and bread because bread and milk already came. So you don't need to write 2 times that. So all combinations of these frequent item sets only taken now.
Right.
Then pairs of 2 item sets. So no need to generate candidates involving Coke or X because they are infrequent. So when you get the 2 item sets, what are becoming infrequent here?
Milk and
Bread
beer,
and beer, milk and beer are infrequent. Ignore them now to extend to the 3 item sets. Then here 3 item sets are given. When you find all 3 item sets, ignoring these infrequent things, you are getting how many now in 3 item sets? How many have support?
None.
Nothing has support. Then you don't need to extend, right? You can also make 4 item sets, 5, but they will become anyway infrequent. So if you do the original formula, 6C1, 6C2 plus 6C3, 3 item sets. We are coming here, let's say, to see 3 item sets. Then you are getting 41 in the original formula. But if you use this pruning method, then we got 6 for the first time, then 6 for the 2 frequent item sets, and 4 for the 3 frequent item sets. Total is 13. So you are able to reduce from 41 to 16 in the first step. After 3 item sets, it has become 1. Okay. What is this 2? Okay. Triplets is 3 item sets. We'll see anything will come next. What is this 13? This one is singling out. Maybe is did he put anything condition on? We'll come back when that is described. So this a priori algorithm putting stepwise, Fk equal to the terminology Fk means capital Fk means frequent k item sets, small lk means candidate k item sets. Candidate k item sets means which are eligible to be processed further. Fk means how many are possible that frequent k item sets. So algorithm let k equal to 1, generate F1, all frequent 1 item sets you need to find out in the beginning. Repeat until Fk is empty. Candidate generation, generate Lk plus 1 from Fk, means which are satisfying our rules. Out of the Fk, they are called Lk plus 1, means going further. Candidate pruning, prune candidate item sets in Lk plus 1 containing subsets of length k that are infrequent. See here, F1 is how much here? All this set is called F1, bread, coke, milk, beer, diaper, X. Your Lk plus 1 is you need to add elements to these things. Then bread and milk, bread and beer, bread and diaper, these things. In this again, you will eliminate some of the things. So generate F1, repeat until Fk is empty, candidate generation, generate Lk plus 1 from Fk, candidate pruning, prune candidate item sets in Lk plus 1, containing subsets of length k that are infrequent. Support counting, count the support of each candidate in Lk plus 1 by scanning the DB database. Candidate elimination, eliminate candidates in Lk plus 1 that are infrequent, leaving only those that are frequent implies Fk plus 1. So we'll take example and see. So candidate generation, brute force method this is. Brute force we know. Then candidate generation, merge Fk minus 1, F1 item sets. Okay, so we will have here in candidate generation, if you take the brute force, all three items, 6C3 will come, right? What is 6C3? What is the number of 6C3? 6C3? How much the value of 6C3? 6 into 5 into 4 by 1 into 2 into 3.
26.
3 to 24, right? 6, 20. So
26.
is it our, so this will have 20 elements. Now count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remaining are 10, right? It is almost middle. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if you use the brute force method, you need to take all combinations 6C3. Then candidate pruning, only one set has become bread and diaper, milk has become the eligible thing after this. Then frequent item sets, if you find here, beer, diapers, bread, milk, diapers and milk, only you can extend each one with how many? These frequent item sets are only 2. So we will extend only those frequent item sets. So we will take frequent item set, frequent 2 item set, frequent 1 item set. We will not join all possible things. So once we get the frequent 2 item set and we get the frequent 1 item set, only combinations will be eligible to find out the frequent 3 item sets. So you take here frequent 2 item set, which is given here earlier in this, then join with the F1. So merge Fk minus 1 and F1 item sets. Then you get a rule Fk minus 1 to F1. So here candidate generation item set. So beer, diapers. Then how many ways you can add beer diapers? Beer is there, so there is no meaning of adding that. Then bread, beer diapers and bread is the first one. Beer diapers, you can also add diapers, but already it is there. Second is beer diapers and milk is the second one. Similarly, you start with the second one, bread diapers. Bread diapers, beer will come, but that is already there. So that won't add anything. So if you do like this, it's each combinations, remove the duplicates, you'll get only 4 out of these things. Then candidate pruning. After this, which are actually having your support after getting these 3. This is candidate generation, LK plus 1. This is means next level. After pruning, you will get FK. So generating and pruning candidate K item sets by merging a frequent K minus 1 item set with a frequent item. Note that some of the candidates are unnecessary because their subsets are infrequent. So this is important to understand now why we are trying only with the 1 frequent item sets to find the FK. See, this becomes a superset, right? Whenever you are adding beer diapers with another element, beer diaper and bread, suppose. Bread itself is not frequent. Then any superset of frequent, any superset of the infrequent one will not become frequent. So if as a single subset, as a single item set, if it is infrequent, there is no meaning of finding any superset of this becomes a frequent subset. So to get the 3, you know that already these 2 are frequent. Then you can only add one more element to that, which is already frequent. If that itself is not frequent, the combination will become anyway infrequent. That is the necessary condition we are getting. A 3 item set to be frequent, we are adding with all 2 item sets frequent with the 1 item set frequent. But there is no guarantee that when they are coming together, they will become frequent. But there is guarantee that it's a, if 1 item set is infrequent, if you add that to the 2 frequent item set, because that becomes a superset of the 1 infrequent item set, that becomes infrequent. So to find the kth frequent item sets, we need to add Fk minus 1 with all 1 frequent item sets. You understand this logic or not?
Yes, understood.
Because when you are combining, that becomes a 3 item set, but that is also a superset of that 1 frequent item, 1 infrequent item set if you combine with one infrequent one. So anyway, that won't become frequent. So that's why always it's a, first we got the F1, then we are getting F2. To get the F3, you already know that what are the 2 frequent item sets. You need to add one more item. If you add that one more item, which is frequent, there is chance that as a 3 item set that may become frequent, because we don't know that it's how many transactions will support they come together. But if you know the single item which you are adding to the 2 frequent item set, if that is infrequent, the 3 item set also will become infrequent. That's why we don't need to add infrequent 1 item sets. So always to get the Fk, you need to have Fk minus 1, then try out and see that all 1 frequent item sets. And when you add them, they may become frequent, they may not become frequent. But you need to compute them and prune them, which will become frequent, which will not become frequent. So another type of thing is, instead of adding with Fk minus 1 with Fk, we can also do Fk minus 1, Fk minus 1 method. How much it will give when you add Fk minus 1, Fk minus 1? K minus 1 item set, adding with another K minus 1 item set. So here we will see that this example, frequent 2-item set, frequent 2-item set. Then candidate generation, item set, maximum how many, how big item set you can get when you are taking 2-item set combination with another 2-item set? 4. But
maximum of
yeah, but what we do is up to k minus 2 elements or up to 1 element less, they should have the same. Only the last element should differ. Then only we will combine them. Like here, beer and diapers, they is the same item set. We don't do anything. We will see that for which item sets in the second one, beer is the first element. So only for one, right? And the combination is same, so we don't get anything. Then we will take the bread. Bread is coming 2 times. Bread diapers is there. Bread diapers, that is the same set. Bread, whenever the first set is same, we will combine the second elements. First element is same, we will combine the second elements in this case. So bread is same for bread diapers, we will eliminate. We have bread diapers and bread milk. So we will add bread diapers and milk. Means last but one element should be same. Then we will generate FK by adding the elements at the last position if they differ. If they are same, then you will get the same item sets. That's why you won't add. So bread is same for in the second row for the first transaction, third row in the second transaction data set. So we are getting bread, diapers, and milk. Then if you take bread milk is same. Bread milk diapers already has come. So we cannot get anything here. And diapers is same, but milk is same. Only one set you are getting here. So another way of joining is up to, you take Fk minus 1 item set and Fk minus 1 item set. Join only those items which are differing at the last position in that item. Means first you should order in some ordering way so that you don't get confused. So sort them from items. You'd say you number them instead of beer, diapers in algorithm 1, 2, 3. So always the item set should to be represented in a sorted items. So once you get that sorted, up to k minus 1 means if you are taking k minus 1 item set, k minus 2 element should be same. Only last element can differ. Those elements you will add to get the FK, because k minus 1 element, k minus 2 elements are same. 2 more elements you are adding, the last ones. So you will get FK set. Then always it logically will give a possible frequent item set of k.
Can you repeat the question?
Earlier we got understanding that when you are adding one frequent item to the k minus 1 frequent item set, there is probability that may become k frequent item set, right?
Right.
Again, we will verify there is only probability. In other way, there is absolutely zero probability. We are eliminating, right?
Right.
Here, we are taking 2 k minus 1 frequent item sets, which have same elements up to k minus 2. And we are adding k minus 1 of the first frequent item set, k minus 1 element of the second frequent item set. Means 2 elements we are adding to k minus 2 same elements. So we will get the k item set. So that may become frequent. Why? Because at least their subsets are frequent, right? When you remove the one element, their subsets are frequent. That's why there is probability that if it is k minus 1, fk minus 1, all its subsets are frequent. Another fk, all its subsets are frequent. You are making the k item set if you want to make the k item set frequent, its subset should be frequent. That is what we are taking care that here. So it subsets, removing that last element and two elements you added. If you remove the last element, this is coming from the first one, so that is anyway frequent. And if you remove the last but one, that is coming from another transaction data set, another frequent item set, that is also frequent. So you are making sure that it's fk minus one subsets are frequent. When you are forming the kth item set, its k minus one subsets are frequent. And recursively, because those k minus one sets are frequent, then k minus two subsets are also frequent.
Right.
So that is what we are taking care, so that it's there is probability that they become frequent because their subsets are frequent. If the subsets are itself not frequent, then we don't add them. Okay, merge two frequent k minus one item sets if their first k minus two items are identical. So F3, ABC, ABD, ABE, whatever that, something is given here. Merge ABC, ABD, provided these first two elements are same, then you are getting ABCD. So now tell me how many subsets you can find. You will be able to find from ABCD. 3 subsets. You can find ABC, ABC, ABD, ACD, then BCD. 4 subsets you can find, right? 3 subsets for this.
Right, of length 3.
So anyway, if you eliminate D, then ABC will come. If you eliminate C, ABD will come. But ABC, ABD anyway frequent, you know that. So what other things you are getting? You are getting BCD.
BCD.
Whether BCD is frequent or not, we don't know that. We need to compute. But anyway, BC is frequent, right? From here. And BD is also frequent. Only the question is whether CD is frequent or not. So at least some of its previous subsets are 3 subsets should be frequent. That is what we are using here, the idea. So if they are not frequent, because they are subsets, right? ABC and ABD are subsets for ABCD. If these are not frequent, then there is no meaning of adding this. That is what the idea here. So do not merge ABD, ACD, because they share only prefix of length 1 instead of length 2. So these we will not add because they are sharing only length 1. So we are adding 2 more elements. So instead of this, you go for the 2 elements things, then make the 4 element thing. 3 elements to 4 elements. Only if they share the prefix of length k minus 2, not k minus 1 or 1. So let F3 equal to ABC, ABD, ABE, ACD, all these things with a set of frequent 3 item sets. Then L4 you find. Okay, compute now L4 from this. How are you getting ABCD?
ABC and ABD from those 2.
Because AB is common, right? Only last elements are different. Then how are you getting ABCE?
ABC and ABE.
Is there. And how are you getting ABDE? ABD you have. Then ABE you have anyway.
Yes, beside itself. ABD, ABE.
ABE. So you are getting this. So can you get any other things? BC is there anywhere? BC is there nowhere, right?
No.
Then AC is there nowhere. You are getting any AC. So like this, you are getting frequent item sets by merging Fk minus 1 to Fk minus 1 kth frequent item set. Then L4 is ABCD, ABCE, ABDE is the set of candidates. L means what? What is difference between F3 and F4 or L4 and F4?
L4 are probable candidates, F4 are frequent candidates from that.
So after L4, we'll get the F4 by getting the support count. So first, we will get only L4 from F3. L4 will be converted into F4 by eliminating infrequent items. So prune ABC because AC and BC are infrequent. Prune ABDE because ADE is infrequent. Okay. Anyway, you have 3 frequent item sets. Once you get the 4 frequent items, then it's a prune ABCE because get its subsets ACE, see whether that is available in FK-1 or not. If that is not available, then you can prune this. Similarly, BC, they are infrequent, so prune them. Finally, you got F4. After candidate pruning, L4 will become ABCD. Only one is having enough support. You understood why they are removing ABC and ABDE?
So will they check their subsets or will they check in the database directly, the support count of ABCD, ABCE, and ABDE?
No, they need to get that, right? By eliminating this one element, you get ACE. From ABCE, only one element you remove. By eliminating one element, you'll get subsets, right, of size 3. Whether they are there in F3 or not, that is what you're checking here.
Okay.
See, if you eliminate either C or E, anyway they are available in these things because you are coming from there only. So you need to keep these 2 elements compulsory, CE. You understand what I'm saying? These are the elements, right, which you are adding. Then remaining elements only you need to take one by one out. Because any other thing other than E, that is infrequent, right? In ABC, any other than C or other, because ABC is there and ABE is there, that's why you are coming here, ABC. Now putting together CE and removing 1 elements, don't remove this C and E, then remove 1 elements and C. So if you take out 1 element out of CE, then that anyway is frequent because you formed this from ABC and ABE. So that's why they are taking out ACE and BCE. CE should be there. Then similarly, ABDE, DE should be there in both. Then you can find ADE and BDE, but ADE you don't find in F3. That's why it is infrequent. This is the superset of ADE, so it also will become infrequent.
Right.
So alternate FK-1, FK-1 method, how we do this, merge 2 frequent K-1 item sets. If the last K-2 items of the first one is identical to the first K- items of the second. This is what exactly we did now. Then F3, again you find ABCD, ABD, ACD, BCD. Merge
doing in a different way, sir.
This, okay. Merge 2 frequent K-1 item sets. If the last K-2 items of the first one is identical to the first K-2 items of the second. Okay. Just they change it. The first ones and last one can differ.
Yes.
Right?
Instead
Both
of
are same. So one end should differ, that's all.
Right.
Ends can differ, but not the middle elements. Here BD, BD is same. Then first end or whether this end or that end can differ. Candidate pruning for alternate FK-1, FK-1 method, then again be the set of frequent 3 item sets. Then L4 is given is the set of candidate 4 item sets generated from previous slide. Same, they are trying to explain. Not only they differ at the last element, they can differ at first and last element also. Okay. Then illustrating this a priori principles, then we are trying to get frequent item sets of 1, then frequent item sets of 2. Then we got this with support based pruning, we got 13 here. This is what we computed already. So how you got 13? Earlier we got 16, right? By using this fk minus 1 combination with fk minus 1, you are getting 13. Use of fk minus 1 method for candidate generation results in only one 3-item set. This is eliminated after the support counting steps. So from here, when you use the fk minus 1 combination, you are getting only 13. Earlier we got 16, right? By using a priori principle.
So that was before pruning. I think after pruning,
No.
we get
That is fk minus 1 and f1.
F1. Oh,
So fk minus 1 combination. This is. Scan the database of transactions to determine the support of each candidate item set. Must match every candidate item set against every transaction, which is an expensive operation. Now we are trying to, that is how to reduce the number of frequent item sets to be explored. Now we are looking how to scan the, how we can reduce the number of transactions to be compared. So scan the database of transactions to determine the support of each candidate item set. Must match every candidate item set against every transaction, which is an expensive operation. To reduce number of comparisons, store the candidate item sets in a hash structure. So here a data structure is given. So you can store them in a hash structure so that you can reduce your support count or comparisons. So what we do is, we'll discuss this tomorrow. So we concentrated today how to reduce number of candidate sets to be explored, right? Whether they are to be frequent or not. That is the first step. The second step is how do we reduce the comparisons? That we will discuss tomorrow. So as I repeat again, it's these things to be done with examples and understand. So please take pen and paper and see that it's how they are computing from fk minus 1 combination fk minus 1 to fk, those things. So it may not come with one listening or one time reading this. So you need to put good effort. Of course, it's finally you will get a package to find out a priori principle and get the all association rules, provided you give those two parameters. What are those two parameters to be given for associate rule? What required to say whether it is a qualified association rule or not?
support and confidence.
Confidence. If you give those two parameters, then there will be a package which will find out from a database of transactions all association rules. So finally that you will do. But what is the use of understanding how they are computing this? You are not going to write that code, right? Usually.
Right.
What is the fun in this understanding these things?
We'll know what's happening internally.
Yeah, if you want to change the algorithm at any time, then you can change the algorithm. And how much you will also get in advance to know that when you are using that package, how much time it will take.
Right.
Of course, the implementation you may not know, but the best implementation also will take this much of time. You will have some idea, right? Then you will not get agitated if it is taking too much of time. Because we haven't come down mathematically to anything less than the exponential yet, if you remember.
Right.
We haven't proved that we are only trying to use different methods. These are still exponential methods only. There is no guarantee that whenever it is two frequent item sets, suppose all three item sets also may become frequent. We don't know if that data set supports. So these are exponential algorithms that at least we should understand. In exponential itself, but in reality, they won't be exponential. Theoretically, you may prove that it is exponential, but in reality, there will be very few transactions which will qualify to be association rules or frequent item sets. So we should have that idea. Only if we go through this idea, we will get. And we will also learn how people develop different algorithms when such situation comes. You may not require exactly association rule type of things, but if you define something different, then you may use these ideas, how we implemented this association rule, what data structures we use it. So for this context, how do we use the same thing? So that will help us to think and learn it, see, to create new algorithms whenever new problem comes. Unless we go through these, how people are implementing, then we will have nothing. Earlier, there was complaint that from the companies who hired MSIT people, they were coming back and say, your students are good, provided if the same code is available in Google for some similar problem, they will search and get that code and somehow they will finish the problem. But if that is not exact problem, they don't think how to solve that. So conceptually they are weak. That is what some companies, they reported back. Why this conceptually weak means not going through how these algorithms are working, how they built these algorithms, what problem they are solving. When such situation comes, then how do we think to solve that? That actually develop your problem solving skills. After some time, whatever can be repeated, like search and paste the things, that also can be automated in future. It's the easiest thing to be automated, to find out whether this problem is same, only parameters are changing. So you just change those parameters and get. Almost your packages are doing that. And little bit you are adding. So that's why we are still interested to see at least the ideas. If you don't understand from end to end, it's okay. When that is required, you will sit and try to understand each step. But overall picture, you need to get association rules, how they are implemented, what are the important things there. Then he listed out first complexity. Complexity is coming from N, the number of transactions, then M, the number of possible frequent item sets, and W. So then all three, how can I reduce that? So that is the logic which he is actually developing as a story. So whatever problem comes first, how do we estimate the complexity? Then second is, how do we reduce that complexity? So that approach is also important. That is what we are trying to learn from here. Apart from what is the association rule, where do we use these things? So if you can catch these things, intrinsically, how these algorithms are developed, then you'll become a good problem solver. That is what I'm hoping. That's why I'm discussing in detail these algorithms. Though there are packages which you don't need to know the algorithm, just use the package. Okay, I'll stop it here. I don't think immediately you'll get lots of doubts, but when you go through this, you may get doubts. Then again, you can come back tomorrow. We'll discuss those doubts.